Hello, everybody. In today's live, we're going to continue where we left off yesterday. Let me grab that real quick. So, yeah, we're talking about Riemann sums, the Riemann sum formula, and why it makes sense. We're going to continue with that today, but we're going to get more specific, basically. We're going to talk about how to actually solve Riemann sums with actual numbers involved, not just not just for the theoretical purposes, not just in general, but we'll get specific. So that's good. Just a second here. So let me put this in. So yeah, so let me share my screen. So where we left off yesterday, and let me actually make a quick note real quick. So yeah, so basically where we left off yesterday, let me share my screen first. So we talked about kind of the Riemann sum formula. We talked about like just in general. Again, or yesterday we didn't any specific numbers per se. We just talked about kind of if you have basically A being a starting value, B being the ending value, and you're trying to find the area under that curve. And let's say we have n rectangles, so we did everything very abstractly, but we talked through some of the formulas and why they make sense. So we talked about how to find delta x. It's basically the entire distance b minus a over the number of rectangles n. That's what delta x is if delta x is the same for each. And then we talked about the various formulas to actually like systematically calculate the left, or the midpoint rule within each partition. And these are basically formulas that if you just plug in k equals 1 or 2 or 3 or whatever partition you're in, you just plug it into those formulas, that will automatically put you at the right x value to do the sample point that you want. So that's what we talked about yesterday, but this is all very abstract. So today, what I want to do is I'm going to copy this in actually to our today's board because I want to build off of this. Um, but bringing this in here, if it lets me upload it, there you go. So looking at this, again, we talked through all of this and what it means, but of course it's all very abstract. So here, what I want to do is make it a lot less abstract. So what we can do is, first off, let's not even talk about. I won't even bring up the integral. We're getting close to the integral here, very close. But here, what I'll do is let's just talk about the actual problem. So like an actual realistic problem here. And I won't make it too complicated, but let's say I don't know. Let's say we want to find the area under the curve, basically sine. I'll just make it up. So find the area under the curve, and then what's the curve going to be? We'll say f of x is equal to, let's see, what do we want to do? I'll just say, I'm just making this up really, sine of x plus 1 minus x squared, let's say. Actually, let's not do sine because that'll be harder to calculate by hand. Yeah, so you can do sine. It's just you have to be able to calculate it for anything. So let's just say let's do this, and actually let's change it slightly. Let's say 5 minus x squared, and then let's say, so the way the problem would be listed is find the area under the curve f of x, where f of x is at, between x equals 1 and 3, let's say. Or actually, let's say 1 and 2. Yeah, or let's say -1 and 2. How about that? So between -1 and 2, using let's say three partitions. So three, yeah, partitions with, and then we'll do all of them actually. We'll do the right. So we'll do the right Riemann sum. We'll do the left Riemann sum, and then we'll also do the midpoint because each one of those changes, right? So like we have different formulas. We pick different x values for each, so you can kind of imagine. And I'll show a good visual of this later on too throughout the problem. But we'll kind of go through each of these if that makes sense. So that's good. Now let's actually talk through this. So how would we actually do this? So in practice, basically what we'll do is we'll kind of get started with the general formulas, right? So the visual, and again, this is kind of the benefit of this method is you don't really need to even think about the specifics for the problem you're dealing with. That's kind of the benefit of this. We can just have this visual in our head regardless of what the function is. Even though the function is going to look completely different than this, and the a and b value will look completely different, you can think about it like this. So if I use this, and actually let's just start off with the formulas here. So the first step with when you're doing Riemann sums, and again, to be clear, let me also specify. I should say you should use a different word here. I should use the word approximate the area under the curve, because what our answers are going to be here are not going to be the exact area under the curve. We'll talk about how to do that later. It's a little bit more complicated, but right now we're talking about the approximate areas under the curve. So these are all approximations, and they're all slightly different approximations, and you'll be able to see as we go through how they're a little bit different. So we'll do that. And then, so let me get that out of the way. And then next, what I'll say is you always have to start with delta x, right? And actually, let me change this slightly. Let's say we use 6 partitions. It'll be a little bit more work, but we'll do that. So 6 partitions. So the first question is, what is delta x in this case? How do we find delta x? Remember, delta x is the width of each individual partition. So what we do is we find the width of the entire shape, like b minus a, for example, and then we just divide it by the number of partitions. So hopefully it's clear that for this problem, so delta x would be, or b would be 2, and then we subtract -1. So 2 minus -1 will be 2 plus 1. And then what's n? N is the number of rectangles or partitions. So that'll be 6 here. Hopefully it's clear. That'll be 2 minus -1, which is 3, over 6, which is 1/2. So delta x equals 1/2 here. So that's the first part. And then after you've done that, and by the way, one thing I'll say, you can think about it like this, like if I literally use this formula, so if I literally use this formula here, which is what we're talking about, but I just replace the n with 6 basically. So instead of, I'll just rewrite it slightly. Actually, I can get away with not doing that. Let me yeah, so if I just replace this with 6, that's the n. So that's the number of partitions. And if you remember what summation notation means from a couple days back, basically what it means is you just start at k equals 1, plug it into the formula wherever it shows up, and then do plus, increase it by 1, and do it again. And just keep doing that until you hit that, and that'll be the last term. So what this would mean is you would have f of x star 1 times delta x plus f of x star 2 times delta x. And we just keep counting up like that. Like the only thing that's changing each time is this k value, and we're just going between the next term. So f of x star 3 delta x, and you see where this is going probably. So let me make a little bit more room. Let me shrink this down slightly. So yeah, plus f of x star 4 times delta x plus f of x star 5 times delta x plus finally the last one, f of x star 6 times delta x. So you can see the value here, hopefully, of like the summation notation. Like my hand's getting tired from writing the same exact thing 6 times. It's kind of useless to do that. Like we can systematize it, and we have systematized it with summation notation. But these two things are the exact same thing. So whenever you see this, think of it like this. But this is only 6, right? Just imagine how annoying it would be if we had to write 1,000 terms. And if you think that's overkill, by the way, we're actually going to do something like that here soon. We're actually going to, well, it's actually going to be even more than 1,000. We'll talk about how to do that when we get there. But anyway, and I know we talked about this yesterday as well. Your life gets a lot easier, right? Because like technically the width of each partition does not have to be the same according to the official definition of the integral, but your life gets a lot easier if it is. So if it is, one, you can use this formula, which we've already used. So we're kind of already for this problem assuming that the delta x is the same for each. That's one thing. The second thing is that if it is the same, look at what we can do here now algebraically. We can say that the area is now approximately equal to, I'm just going to rewrite these. I'm basically going to factor out delta x from every single term. So instead of like multiplying, it gets rid of like half of the steps if you do that. Because then you don't have to do all these multiplications. You basically you just add up all the y values or the function values, function outputs at all the different spots. I'm just going through and doing that here. So f of x star 4 plus f of x star 5 plus f of x star 6. So we just add all those up, and then at the end, just multiply by delta x at the end. So there you go. That got rid of 6 or 5 of the multiplications that you're going to have to do. So that's good. So this is our general formula. Like this is how we find that area under the curve. And again, really, this is just a different way of writing out the area of all these rectangles. Now, here's where the interesting part kicks in: is that they're kind of asking us. Remember, I'm kind of asking us for 3 different scenarios. One is when we're doing the right or the right Riemann sum. The next one is when we're doing the left, so the left, and then the last one is when we're doing the midpoint. So we'll do one of each of these because remember, things do change a little bit. But here's the good news: the only thing that changes is the x star, like the sample x values. The function is the same, the delta x is the same for all these. So what I can actually do, if I copy this down, we can actually get more specific because we already know what delta x is. So we already know what delta x is. It's 1/2 that we found that above. So you can plug that in here if you want. Now, at this point, this is where it gets a little bit trickier. Again, you can use these formulas to be clear. So if you want to do the right Riemann sum, you can take this formula and think about it. Let's think about it for this case. What is A? Remember A, like if you want to find a specific value. So x star 1 is equal to A plus delta x. What did we say that delta x is? Actually, A plus delta x. A is -1. Delta x is 1/2. So what's -1 plus 1/2? -1/2. So you can do that. And you can use that formula. That works. That's valid. But I almost prefer not to. I almost prefer to just kind of visualize it. Like you don't need to redraw this entire thing. In fact, I recommend that you don't. What I would recommend is drawing the bottom here, just to like make sure things make sense to you, like in terms of the x-axis specifically. So if I copy this stuff down, so actually, yeah, let me copy the problem so we don't have to keep scrolling. So remember what we said above. We said that we said that this is what we're actually finding. And if you think of this, there's something very simple you can do here. It's basically you just roughly, again, you don't even need to care about the function. That's the beauty of this method. It works regardless of what the function is because we've kind of abstracted that away, right? You can see we have f of here on the outside. Our job is just to find the sample x values, which will be the same procedure every time, regardless of what the function is. So what I would do is I would just roughly draw this. So I would say, okay, if a is -1 and b is 2, and then we're doing 6 equally spaced partitions. Hopefully you can see here visually that, yeah, we're going to split that one there, right? Because three would make, actually, I didn't draw this well at all. Let me bring this in. Well, there, that's more realistic. So 3 equally spaced ones, that would be like if I got rid of, like if I just split them here, right? So 2, like there's a whole width of 3. If we split it into 3 equal rectangles, it'll be that, or equally spaced rectangles. And then if we cut each one of those in half, that's how we would get 6. You can kind of envision it like that. And then when you draw it like this, you just want to make sure that your visual, like once you have this rough visual of like the x values in particular, then you're in a good spot actually, because think about it. So now what did we say? When we used the formula, we got -1/2. That makes sense here visually. This is what we're talking, right? This is what we're talking about essentially, the rightmost point in the first partition. That's what the formula gave us. But you can kind of visualize it, like, or you can kind of common sense your way through it, right? If you just look at this and you know that this is the a value, you know that this entire width is delta x, you can just add delta x to that value to get to the right side. So you don't have to use the formula. And a lot of times, like I said, I think it's easier not to actually. But anyway, that's good. So once you have that, now what do? What you could do, again, I don't really recommend this. You could use the formula. You just plug in. So -1 plus 2 times 1/2. So -1 plus 1, which is 0. And just looking at the visual, we can see that that's right. So you could use the formula to get all 6 of these values, Or here's the easier way to do it. The way to do this is basically triple check. So triple check to make sure that you found the first one correctly. Because if you use the simplified technique that I'm about to explain, if you get the first one wrong, it's actually going to throw off everything. And you don't want that. So be 100% sure, triple check that x star 1 actually makes sense for the starting value. And then once you have that, you just add delta x. That's the rule. You just add delta x to get to the next value. So you don't even need a formula here, basically. You just, if you get negative 1/2 right, just add delta x, which is 1/2, positive 1/2, to get to the next one. And then you do it again to get to the third, and then again to get to the fourth, and then again to get to the fifth. So I'll say 3/2 here. And then again to get to the last one, which will be 4/2 or 2. And then when you check it out, doesn't that kind of make sense, right? Negative 1/2, 0, 1/2, 1, 3/2, 1.5, 2. Where like those values are the rightmost sample points of each partition. So that's good. The trick, basically, you just need to common sense the first one by just visualize. Like that's actually, like I said, I recommend not using this formula. I would actually just rather you draw this out, kind of common sense your way to the first one. And then after you're 100% sure that the first one's right, just keep adding delta x to get every subsequent one. That works regardless. Like that doesn't just work on the right, by the way. Like the adding the delta x thing, that works for like the right, the left, the midpoint, as we'll see. So those are the sample points, and that's the only thing that changes in each case. So now, once we have those, we can kind of plug those in now. So now, what is this going to be? This is going to be f of negative 1/2 plus f of 0 plus f of positive 1/2 plus f of 1 plus f of 3/2 plus f of 2, all times 1/2 at the end. Now let's think about it. So what would these actually be? Remember what the actual function was: 5 minus x squared. So here, this is where things get kind of annoying. But 5 minus x squared. In fact, I'm tempted to maybe choose a simpler function. What are we doing? We're going between negative 1 and 2. Now I'll leave it at this. So here, f of 0, that's 5. So that one's easier. And then this one is what? 5. It's 5 minus 1/4 plus 5 plus 5 minus also 1/4. Right? So whether it's negative 1/2 or negative or positive 1/2 squared, doesn't matter. So 1/4 plus 5 minus 1. So that's easy. That's 4. And then 3/2. This will be what? 5 minus 9/4. So like 2.25. And then plus 1. Right? 5 minus 2 squared is 1. Whatever that is. And then we multiply everything by 1/2. So that's good. And then if I make some room here, so if I just pull this down a bit, or whoops. So yeah, now if you combine these, let's see. So 5 plus 5 is 10, plus 5 is 15, plus 5 is 20, plus 4 plus 1 is another 5. So 25. 25 minus 1/4, and 1/4 is 1/2. And then minus, or actually, I'll just leave it as minus 2/4. And then minus 9/4 is, I guess, minus 11/4. And then all times 1/2 on the outside, or whoops, 1/2. And then now 25, honestly, what I would do is I would do, like, if we want to get the answer in an improper fraction, I would get common denominators. So 100 over 4 minus 11 over 4, what's that? And then we'll do 1/2. And then what's that? That's going to be 89 over 4 times 1/2. So hopefully it's clear. 89 over 8, which should equal approximately, I guess, 11.25. So that's the approximation for the area under the curve using the right Riemann sum. Hopefully that makes sense. Now, again, that's just 1/3 of what we need to do here. We need to do the left Riemann sum now. But again, the good news is this formula still remains true. So the formula is true. The same formula is true every time. The only thing that changes is the way we pick the sample points. That's kind of the good news. Like I said, if you want, you can basically use this formula. You can do that. Or what you can do is what I actually suggest. Don't find the formula. common sense your way through the first one. So common sense your way to get the first one. And then after you have the first one, here, let me pull this down slightly. Yeah. So pull that back up. So yeah, common sense your way through the first one. And then after you have it, just add delta x to get all the others. That's my actual recommendation. So here, if we're looking at this visual and we're trying to get the left Riemann sum of the first one, hopefully it's clear that that's just -1. So like x star 1 would equal -1. And then how do you get the next one? Just add 1/2. So the next one is -1/2, then 0, then +1/2. It's actually the same exact values as before, if you think about it, like the same x values. It's just that we get rid of this one and we add a f-1 in front. Hopefully that makes sense why that happens visually. It's because like it's basically because the like for all the interior partitions, interior rectangles, the right side of it is the left side of the next one. So like if we're doing the right Riemann sum, think about what we're gonna do. We're gonna do that, and that, the right of every partition. But if we're doing the left, all these are gonna stay the same actually. It's just that one that's not gonna be included and that one that is gonna be included. That's the difference. Like the -1, 0, 1/2, 1, 3/2, etc. That part is still the same. So once you realize that, again, basically here, we're going to do, f of -1 plus f of -1/2. And then we're just going to count up. So you just keep counting up by half. So f of 0, f of +1/2, f of 1, plus f of 3/2. And then all times the 1/2, or all times the 1/2 on the outside, like that. And then what are these going to be? Remember our function, of course, is still 5 minus x squared. That's the function we're trying to approximate the area under. So 5 minus -1 squared, that's 4. And that's also 4, by the way. And then that's 5. And then we talked about before how this is like 5 minus 1/4. And that's 5 minus 1/4. And this is, I guess, 5 minus 9/4, like that. So 1/2. And then we're adding all these. So think about what those will be. So we'll have what? We'll have 5 plus 5 plus 5, 15, 20, 24, 28. So 28 minus -1/4, -4. So again, minus 11/4. So minus 11/4 again. And then what is that? So if we're again finding a common denominator, so multiply both of these, or multiply the 28 by 4, so that'll be divided by 4. And also, so think about it like this: 30 divided by 4 is 120, and then minus 2 times 4 is minus 8. So hopefully that's clear. That'll be 112. And if you can check that, right? So um, if you basically look at it like this, um, yeah, actually, let me do this. So yeah, if you look at it like this, basically this is just mental math, right? So if you have like 30 minus 2 times 4, just 120 minus 8. That's essentially what we did there. And you can also check it, right? So again, the whole point of doing this is that you don't have to check it, but if you want to just be 100% sure, then as you do this, you basically get what? You get 3, or sorry, no, you get actually 2, and then minus 8, and then you get 32. How many times does 4 go into 32? 8. So yeah, 28. So that checks out. So that's like just a quick mental math thing, not a big deal though. And then over 4, so 112 minus 11, you get 101 over 4, which is 100 over 4 is 25. So it's actually 25.25, 25 and 1/4. So there we go. So it's actually a pretty it's a significant, or actually, sorry, this should not be. Um, oh, sorry, and then we need to divide by 2. I almost forgot. So yeah, I was gonna say that's like 2. That's too far apart. So this whole thing, yeah. So good. 101 over 4, and remember we need to divide that. So 101 over 4 times 1/2. So we need to divide by 2. So it's actually 101 over 8. And then if you think about it, so let's see. So we already talked about 88, and then if we add 8 again, would that be 96? So 96 would get us 11. Or sorry, not 11, 12. So this should be what, 12 point, so I guess 96 and then 12 and 5/8. So 12.625 or 12 and 5/8, however you want to word it. So that's good. So that's apparently the answer. And again, you can see it's somewhat close, right? It's not exactly the same, but it's somewhat close to what we did with the right Riemann sum. And then what we can also do here is we can do the midpoint. So again, you guessed it, like it's gonna stay mostly the same. The only thing that changes, and again, it's sort of a big change, but it's just one part of it that changes, is that the delta x's now change. Or sorry, not the delta x's, the x sample points. X star one, X star two, etc. Those now change. So X star one, think about what that's going to be. Well, here, if this isn't, and then again, this is what I recommend to like common sense your way through it. If this right here, if -1 is the leftmost partition of the first one, and -1/2 is the rightmost of the first one, what's right in the middle of that? Hopefully it's clear. -0.75 or -3/4. So -3/4. And then again, that's all you really need to do. You just need to be 100% certain. You need to be 100% certain on the first one, and then once you put in the rest of them, remember you just get to add delta x to get to the next one. So this will be f of -3/4 plus add 1/2 to this, or think of it like 2/4. That'll be f of -1/4. Add 2/4. That'll be f of +1/4. Then f of +3/4 or +3/4, and then f of, so what is that? That's 3, 4, and then f of 5/4 plus f of 7/4. 7/4 being 1.75, and then all times 1/2. Now here, if you look at this, the question is, does this make sense? So f of -3/4, -1/4, +1/4, +3/4. So it's kind of symmetrical with these because we're actually dealing with an even function. You don't really have to worry about that, but it's true. And then 5/4, 1.25, and then 7/4, 1.75. So yeah, that you see how just that trick of just get the first one right, be 100% certain, just keep adding delta x to get to get the rest of them. Like, because the reason that works, by the way, is like if you get the middle of this partition and you just add delta x, it will automatically put you in the middle of the next partition, and then so on and so forth. And that's the trick that we're taking advantage of, is we just keep adding delta x to each x value. That's important. Not, you can't just add it to the y value because the function might change unpredictably, but for the x value, you definitely can, and that's what we just did. So that's good. So this one will be a little bit more annoying to evaluate, but I'll try. Yeah, it could get worse. But as you can see, you can do these 100% by hand. You don't need a calculator for these. Life gets a lot easier, obviously, with a calculator with these. We don't like doing this, but we can do it. So 5 minus 9/4. Actually, sorry, that's different now, right? So before we were dealing with the half intervals. Now it's actually 9/16. So 9/16 plus 5 minus 1/16 plus 5 minus 1/16 again. So there's a lot of, this is what I was saying before, like the first four are actually like kind of duplicates of one another, at least the left and the right side. But you don't, like I said, you don't really need to care about that. That just makes it slightly easier to add. 5 minus 9/16 plus 5 minus 25/16, right? 5 minus x squared for all these, plus, so plus 5 minus 7 times 7, 49/16. So this is, as you can see, this is a lot more annoying to calculate, but we'll try. So we should have 6 5s, right? 1, 2, 3, 4, 5, 6. So that'll be 30 minus what? What do we have? So 9/16, 9/16. So the good news is, and this is something you should do as you're going through if you can, is like make all the common denominator, make all the denominators common. So we know it's going to be a 16 there for the rest of all these. And then 9 plus 1 is 10. 9 and 1 again, 20. Plus 25 is 45. 45 plus 49. So 45 plus 45 is 90, and it's like we have an extra 4, so it'll be 94/16. And then this is going to get kind of annoying if you do this, but you can do it. So if you, again, get a common denominator on the left, so 16 as the denominator, what's 30 times 16? 480 minus 94/16. So if you pull off a whole 80, you're at 400, and then pull off another 14, that'll give you, I guess, 386. So 386 over 16, whatever that is. I won't simplify it to a mixed number, but I think we did all that right. So that's the process. Now here, so that's what we get. And let's actually check these on Desmos. I actually have something that's really useful here when you're checking this, because like what we're doing now is it's essentially a type of problem. It's essentially a type of problem like where you do what are called Riemann sum approximations, and then you can like there's a lot of like homework problems or like test problems sometimes that ask you to do the process we just did essentially, but and that can be kind of tough. Like you after you do all the work, like it's very easy to make one tiny mistake. So what I have here, I created a tool, a Desmos animation, so that you can it's basically a customized calculator for this type of problem. So if you just pull the problem down, so if you just pull the problem down, just pull the problem down, and then the calculator, you just have to type in like the values of the problem to the calculator and it'll do it correctly for you. So like here, the A value is -1, the B value is 2. We said the number of rectangles are 6. The function itself, we said, is 5 minus x squared. So this is kind of the shape we're looking at it. So this is what we were actually doing, by the way. We could do all those calculations that we did without basically without knowing if we were right, essentially. But like or without visualizing it at all, to be clear. So that's good. So we did these obviously without a calculator, without even visualizing the process, except for like maybe the x values you could argue, but not the function. You don't even need to know what the function looks like. That's the benefit of this method. But when we did that, let's see what happened. So the first thing we did when we did it by hand with the right Riemann sum, we got 11.25. On the calculator. You can control like left midpoint right, left midpoint right. So when I go to the right, you can see we got 11.125. What did we say? We said 11.25. Oh, actually, yeah, I just did the last part wrong. So like one eighth is 0.125, not 25. So yeah, so that's actually 11.125. But you can see everything else we did before that, like that process. That's essentially what the calculator is doing behind the scenes. So that works. And then what's the second thing we tried? We tried for the left Riemann sum. We did all that work and we got 12 and 5/8. 5/8 would be 0.625. So 12.625. And then if we do that, let's go to the left now. 12.625, bingo. And you can see how the rectangles change, by the way, as well. So like for here, the height of each partition is the leftmost value in each partition, right? Where with the left Riemann sum. With the right Riemann sum, it's the right of each value. And that's why the values are slightly different depending on which one we do. And the last one we did is the midpoint. We get 12.0625. I didn't want to deal with this, but hopefully, let's see, it's the same 386 over 16. Oh, and then divide by 2. Yeah, I forgot to divide by 2. So there you go. Once we divide by 2 or multiply by 1/2. Yeah, so that's another good lesson, by the way. It's very easy to get distracted with all this annoying work that you forget, like I did kind of, to multiply by the 1/2 on the outside. But once you do that, then yeah, you get 386 over I guess not 16 now, 32. And then 386, yeah, 386 over 32, 12.0625, what the calculator says. So that's good. But you can see, hopefully it's clear, you can see the process here and you can actually see the delta x, right? So like the width, we're going from 0 here to 0.5 right there for each partition. Like the width of each rectangle is 0.5. Like we have 6 rectangles. This is the visual of what's going on essentially. And this calculator would allow you to basically, this calculator, like I said, all you have to do is you have to plug in the inputs to the problem. And this is what you need to know, all these values, by the way. Anytime you want to do a problem like this, you need to know the function you're approximating the area under, the x values between which you're approximating the area. Because right, if we change the b value, now the area changes, right? So it's like you need an a and b value. It's not just enough to have the function. And then you need to know the number of rectangles. If you're doing an approximation later on, we'll like probably tomorrow, we'll talk about how to actually get an infinite, like get an answer that's like infinitely accurate, or like get the exact area in the curve. This is like I said, this is just an approximation. You can see we're overshooting in some spots, undershooting in other spots, or in other spots. Overall, this answer is not perfect, but it's pretty good. So this is the idea. And by the way, if you want this Desmos animation, I have this in my Skool community. I'll leave the link in the description if you want to check it out. It is paid, but it's pretty affordable. It's just $9 a month. If you check that out, I have a resource. I have this Desmos animation, this resource, plus a lot of other resources in there for a lot of other topics like this that you can use to kind of help yourself through AP Calculus. So I hope that helps. Just let me know if you have any questions. And other than that, I will catch you next time. See ya.